So far, I basically skipped the first few sections of this chapter. We started here at 5.5. We've done 5.5 and 5.6. Today I'm going to do these three, 0.7, 0.8, 0.9. And this really just kind of continues what we started. These are those problems at the end of the chapter. I'm going to use these as the example to explain. Because this kind of covers, it's kind of all those sections together, come together. So this reaction, problem 7.71. I don't know why they wrote it this way. This reactant right here. It's weird. They've got the formula, and then they decided to put the actual structure there. That's weird. But I'm just going to call it C2H2. And they start calling it C2H2 down here. But they do this now and then. I don't know why. When it's a small molecule, they decide to draw it out. But C2H2 is that structure that they have in here. All right, so here's a reaction. I mentioned this the other day. What these numbers, these coefficients, we call them, we've got this reactant, they react and they create this product and this product. And this tells you how, it's really a ratio of, like I said at the end of the class last time, what this reaction really shows you. It does explicitly show you, here are the reactants, here are the products. But there are 6 relationships in this summary form. These coefficients are important. When I have a 2 coefficient like this, that means there's 2 of these, actually. So this is a summary form of this. There's 5 O2s. And they create 4 CO2s. And 2 H2Os. So that's what the coefficients represent. And it turns out you have to have these coefficients there to make sure the formal way of saying it is no matter is created or destroyed, but really it's just saying everything that's on this side has to show up on this side, no more, no less. You can't have new atoms show up that weren't here, and you can't have atoms here that don't show up here. So that's what we mean by balance. Balance means there's the same number of carbons on this side as there are on this side. Same number of oxygens on this side as on this side. Same number of hydrogens on this side as there are on this side. You've got 4 hydrogens there. You've got 4 hydrogens there. 4 carbons. There's the 4 carbons, and then of course all these oxygens. 2, 4, 6, 8. So there should be. Oh, there's supposed to be 5 of those. Oops. Okay. 2, 4, 6, 8, 10. 5 O2s. 2, 4, 6, 8, 9, 10. So that's what we mean by balance. And to make something balanced, you have to play around with these coefficients to make it balanced. Most chemistry classes, it's like they give you this without the coefficients and say, here, balance the equation. But I don't like having y'all do that. It's an iteration. It's kind of weird. You would need matrix algebra to do it the most formal way. I would rather you just focus on, here's what this is for. This is what chemists do with this. Once it's balanced, there's a lot you can do with it. So this is kind of a summary form of this. We just use coefficients to denote the number of things that are there. So going through these questions, how many moles of O2 are needed? So there's the O2. How many moles of O2 are needed to complete the react with 5.00 moles C2H2? So you put that much C2H2 into this reaction, and the question is, how many moles of O2? I said at the end of the class, last time, that there are 6 relationships buried in here. There's 2 moles of C2H2. So using that coefficient, and we just do it in moles. 5 moles of O2. This is the label. So that's one of the relationships. But I could also do that relationship, that relationship, that relationship, that relationship, that relationship. It's just all the combinations of all the pairs that you could make. It turns out there's 6 total. So there's one of it. And usually when you have a problem to solve, you only need one of those. Sometimes 2, but most of these are just, you only need one of those 6 relationships. And in this case, that's the one we need because it's C2H2 and O2 that we're trying to relate to each other. You might use it like that, or you might use it flipped over, but it's just that relationship. So I'll go ahead and write that down. And then when you solve the problem, the first thing you want to write is 5.00 moles of. So that's how much is put into this particular reaction. But now you grab this relationship and you, okay, moles of C2H2 needs to be on the bottom, so I'm going to flip that over and go 2 moles to 5 moles O2, and that'll result in some number of moles of O2. And this is what we're being asked for. How many moles of O2? These are always exact. So when you're trying to think about significant figures all come from here. That's exact, exact, exact. So we're going to want to be in 3 significant figures. So from there, 5 times 5 divided by 2, I guess that's 12.5. So the answer is that's the answer to A for 5.74. Simple, right? How many moles of CO2 form 6 moles? Okay, so for B, we're being told how many moles of CO2, so this was the question, how many moles of CO2 form from 6.0 moles. So now it's that's not the relationship we want anymore. It's these two we're trying to relate, so we're going to use this. So that relationship's going to be involved. And then they're told us 6.0 moles. Moles of C2H2 needs to be on the bottom. Two to 4. And that'll put us in moles of, what did I do? CO2. It's 4 moles of CO2. So 6 times 4 divided by 2. 24 divided by 2 is 12. Did I do that right in my head? And it's 2 significant figures, so the 12 is what we want. Makes sense? Right. How many moles of H2O are formed from 0.5 moles. So this time we have, so this is C. This is now one significant figure. And we're being asked for moles, question mark, moles of H2O. So every one of those A, B, C, and D are involving this, but you don't have to only involve one every time, but they're just sticking to that. 6 mole, oh, okay. So we're relating H2O and C2H2. That again, and now it's 2. You could sort of reduce this fraction. I never think that's worth doing because you're going to do it in your calculator anyway. 0.5 moles. C2H2. And again, this needs to be on the bottom. That puts us in moles of H2O. It's obvious this is just going to be 0.5 because this is essentially one together. The next one we're relating to CO2. This one is saying how, so now this time this one's the question mark. How many moles of this needs to react to make 0.80 moles of CO2? And that's two significant figures. 2 moles of this to 4. That's the relationship we need. We have 0.80 moles of CO2. I want CO2 on bottom, so I'm going to say 4 moles. 2 moles. And that leaves us with the units of moles, C2H2. It's going to be 0.4. 0.80 times 2 divided by 4. My calculator says 0.4, and I just wrote that down. Is that right? There is a problem. This is only showing one significant figure, so I have to put a 0 here. Now it's correct. 2 significant figures, 2 significant figures. Simple, right?
With the other numbers, you're not looking at
Those are
because they're
exact.
exact. Okay.
Exact, those are all exact. Whenever you see a reaction written with those coefficients, they're always exact. So all your significant figures came from here. All right, a twist on this. I just did the one that gives you answers. You're given the answers to. Shouldn't have done that. This time I'll do, so you get the answers to the odd ones. If I scrolled way down, the answers are there. But you're not given answers to the even ones, so let me do these instead. using the balanced reaction for sodium and water for 5.72. So it's this reaction. So let me write that reaction down. So now our reaction two NaOH plus other products, H2. This book just does weird things with the subscripts and superscripts. But that's what that says. I should mention this, that the S there means solid. This was in a solid form. The L means that H2O was in a liquid form. We haven't talked about dissolving things in things, so I kind of ignore these so far. Aqueous just means it's NaOH dissolved in water. H2 is G for gas. But as far as what we're doing right now, that stuff isn't needed. I'll squeeze that stuff in at another point. All right, so that's the reaction we're dealing with. And we're at 5.74. So 5.74 A, how many grams of NaOH? Question mark, grams of NaOH. From 3.0 moles of Na. All right. This tells us, since we're talking about grams now, this tells us that we're going to need, this is from an earlier section. So sodium, we have one of them. Oxygen, actually we have one of everything here. You would look at your periodic table, look at sodium, and this number 22.99. Oxygen on there is 16. Hydrogen is 1.01. And of course, these are all times 1. These numbers are going to be exact as well. These are the numbers that go into the formula. So 4 significant figures, 4 significant figures, 4 significant figures, 4 significant figures, 3 significant figures, 3 significant figures. Now addition subtraction rules. Addition subtraction rule is where you're looking after the decimal. So this has 2 after the decimal, this has 2 after the decimal, this has 2 after the decimal. So I have to add all these up, I have to have 2 after the decimal. 22.99 plus my calculator says, that's what my calculator says, 40. But, of course, I have to do this. So it's 40 grams per mole NaOH. So let's stick that up here. So 40 grams and 1 mole for NaOH. So you have to do that to solve this problem. And now I'm going to go. The relationship I need here is the one between Na and NaOH. That's going to be 2 moles of Na So I'm gonna need this, and I'm gonna need this, but of course, I tell y'all to do this before you use it in math. That many grams NaOH over 1 mole NaOH. Moles of Na, I've got moles of Na on the top here, so I'm gonna put it on the bottom. 2 moles of Na, 2 moles. Now I've got moles of NaOH on the top, so I want moles of NaOH on the bottom, so it's gotta be 40.00 grams. And if you look at the units, that cancels down to grams of NaOH, and that's what we were looking for. So the rest is your calculator. 2 significant figures, exact. This has 4 significant figures, but this forces us to have to put this in 2 significant figures. Answer there. 3 times 2 times 40 divided by 2. My calculator says 120. And as long as I don't put a decimal here. Oh, yeah, 2 significant figures. This is showing 2 significant figures right now. If I put a decimal here, I'm trying to say 3 significant figures, but I won't put a decimal there. That's the answer. So you have to put 120 grams of NaOH. If you had 3 moles of sodium react with water, you'll get 120 grams of NaOH. 3 times 40 is 80. It seems wrong. Oh, 3 times 40, yeah. Does that make sense? Okay, B on 5.74, how many grams of H2 are formed from 3 moles of NaOH? So I can leave that 3 moles there. So 3 moles of sodium, and it wants to know grams of H2. So H2, you've got 2 hydrogens. 2 hydrogens times 1.01, that's what you get off the periodic table. So that's the grams per mole for H2. So, all right. Grams H2 to 1 mole of H2. So we're going to use this relationship. And then we're also going to use 2 moles of Na. And that's 1 mole H2. So 3.0 moles of Na on the bottom, 2 moles Na to 1 mole H2. Moles of H2 needs to be on the bottom, so 2.02 grams of H2. That's 1 mole of H2. So the units cancel down to grams of H2, that's what we want. Grams of H2. Exact. 3 significant figures, 2 significant figures. So this has to be 2. Three times 2.02 divided by 2. 3.03. That's what my calculator says, 3.03. But it has to be 2 significant figures, so I'm keeping those 2. The 3 does not round anything. So that's the answer, 3.0 grams of H2. This is approximately 2, and if it were 2, these 2 would cancel, and those cancel, so we just get 3.0 back. How many grams of H2O? Oh yeah, H2O. Where's the H2O? All right, C for this problem. Wants to know how many grams of H2O. So to react completely with 0.2 moles of Na, 0.20 moles. So now we need, so grams for that is oxygen, there's 1 of them. Off the periodic table, that's 16.00. Hydrogen, there's 2 of them, times 1.01. 16.00, 2.02. Add those up. (18.02 grams per mole). (18.02 grams of H2O to 1 mole of H2O. So I'm translating this into that to use it. So there's that. That we're going to need, and we're also going to need 2 moles of Na, 2. So we're going to need those 2 things. 0.20 moles of Na. Moles of Na is on the bottom, so 2 moles. Moles of H2O are on the top, so we're going to put moles on the bottom. This is 18.02 grams of H2O. That puts us in grams of H2O. Calculator says that's what my calculator says. But that's 2 significant figures. exact. This is 4 significant figures. So this needs to be in 2 significant figures. The 0 does not round to 6, so 3.6 grams.
Okay, so where did you get the 2 mole of Na over 2 mole H2O, like at the top to the left? So like
2
just-
Na to
just
2
run-
H2O. 2 moles of Na to 2 moles of H2O.
Okay, so then once you get the grams, we got the like 18.02 over 1, you just take, since there was 2 of each, and put those over each other for the
Yeah. This is one of those 6 relationships. In that reaction, there are 6 relationships. You don't generally need all of them, but the 6 relationships are 2 moles of Na to 2 moles of H2O. That's one of them. That's the one we used. And then there's 2 moles of Na to 2 moles. Is it really 2 and 2? Yeah, it's just all 2s here. So I did those 2. Now it's 2 to 1. 2 moles of Na to 1 mole H2. You see what I'm doing?
Yeah.
And then there's more. There's these 2 related to each other. There are these 2 related to each other. And then there's those 2 related to
So
each
you
other.
just chose the first 2.
Just chose the first 2. I used, for this particular problem, I used this one. The previous problem, I used this one. This and this are identical. See what I'm saying? You look at the problem and you see the 2 things you're being asked to relate. H2O and Na. So that's why I grabbed that relationship. The next thing to do is some theoretical yield, percent yield calculations. So let me, I guess we'll do, that's the odd one, so let's do the even one here. So theoretical yield, truthfully, for any of these that we are calculating amounts for products all along here, you could have called that theoretical yield. CO2. So they tell you this is methanol, CH4O. So then when they use the word methanol, you know that's methanol. Theoretical yield. All right. But don't think in terms of the word theoretical yield here. Let me write the equation first. This is end of the chapter 5.78. CO2 and H2O. It's 2 and 4. So they're giving you these so you don't have to calculate them. 2 is 2. CO2 for A, so phrasing this the way those previous ones were phrased, I'm not using the phrase theoretical yield. But I'll put that back in. And I used the formula instead of the word methanol to refer to this. All right, here's how you would do this. We're given grams and we have a result of grams. So grams of CO2 and grams of methanol, that tells you we're going to need a grams per mole for both of those. I don't have to calculate them though because they were given to us in the problem. So this is grams per mole for methanol. This is grams per mole for CO2. All right, the last bit is the 48.0 grams of this. So 48.0 grams of methanol is put in. How many grams of CO2 would you get? So if you set it up like this, you're going to need grams of CH4O down here. This is the grams per mole. So 32.04 grams to 1. So now we're in moles of methanol. And now we're going to use CO2. That's that molar relationship of those six. I'm gonna pull that in there. It's 3324. 230. 2324, did I do that right? 2324. So we got that. So now we need moles of methanol on the bottom. So I've used the 48, I've used the grams per mole for methanol, and then I got the moles of methanol to moles of CO2 next. And next I'm going to use for CO2 44.01. I need moles, running out of room. One mole of CO2 is 44.01 grams. That'll tell us how many grams. You see where I got all this? I'll see where I got all this. So now it's just the math. Of course, grams of methanol, moles of methanol, moles of methanol, moles of CO2, moles of CO2. We're left with grams, which is ultimately what we're being asked for. All right, and then the math. 3 significant figures, exact, 4 significant figures, exact, 4 significant figures, exact. So 3 significant figures is what we're going to need by the end. 48 times 2 times 44.01 divided by 32.04 divided by 2. My calculator says but I need 3 significant figures, so I'm keeping those. The 3 does not round to 9. So. Okay, that, we're calculating how much of one of these two, the things on the right side, the products. When you're calculating how much product you get from the amount of reactant put in, that's called the theoretical yield. I just didn't call it that before. Theoretical yield. That's telling you, theoretically, if you did this reaction and you put in 48.0 grams of methanol, theoretically, that's how many grams of CO2 should be produced, theoretically. And I say theoretically because in the lab, when we actually do this, it's pretty typical to lose a little bit along the way. Typically, you get something less than you expect, theoretically. All right. It's just being tricky by using 48.0 again. But the percent yield now, that's our theoretical yield. And it's saying, what is the percent yield are formed? This, what they're telling you is, they're saying 48.0 grams of CO2 were actually formed. That's what actually happened when someone went and did this reaction. We call that the actual yield. Actual yield of CO2 was 48.0 grams. So theoretically, we expected to get this, but whatever process, whatever procedure they followed, however careful they were or whatever, it turned out this is how much they got. They literally put this on a scale at the end of the reaction and found that. Actually, it's a gas, and you would probably not be putting that on the scale, but you can ignore that. So the theoretical yield is the one that you've got this long walk to calculate. The actual yield has to be told to you. It's just given to you. And then the percent yield, then we always do actual over theoretical times 100. So I could put, I'll put in grams of CO2. And the theoretical was 65.9. But notice the grams of CO2 cancel, so the theoretical yield is always unitless. Times 100.
What? I mean, I survived.
Divided by 65. And we're gonna want three significant figures here. The percent yield,
Oh, did you?
calculator says
I knew it had to.
8, 3, 7, 6, 3, 2, 7, 7, 7. We're keeping three significant figures, the 3 doesn't round the 8, so the answer here is that's the percent yield. Actual over theoretical times 100. And again, actual yield, very easy to know because it's always just given to you. If you're in the lab doing a reaction, and then at the end you're asked for a percent yield, what you weigh on the scale, that's your actual. So again, it's just given to you. Theoretical yields, I think you have to calculate. What else should I do? Think. Okay, so I added in here for the quizzes, these two, the mole and molar mass, I gave to you last time. Now we've done some reaction calculations and some percent yield calculations. Some of those. In that bank of questions I have, they literally only have one on limiting reactants. So I'll probably save that until after break. Let's go up here and see what I can do. One second. So for this, how many grams of CO2? CO2 are formed from 0.5 moles of ethanol. We're gonna need the grams per mole of CO2. That's up there though, 44.01, so I won't go through the calculation. Actually, why not? Question. So this reaction is C2H6O. It's 3O2, 2CO2, and 3H2O. Calculate the grams per mole unless I know we need it. And they told us this from our previous problem, but if you were calculating it, it's CO2, so you've got carbon, there's only one of them, you've got oxygen, there's two of them. If you look on the periodic table, this would be 12.01. That'll be 16.00. Add them up. That's where they got the 44.01. So that's how you would calculate it yourself. These are those numbers off the periodic table. Okay. moles of ethanol. This is ethanol. How many grams of CO2? Grams of CO2. Our molar relationship here, is it a 1? Yeah. So there's a 1 here, it's just not there. So the relationship we're going to need is 1 mole C2H6O to 2 moles of CO2. So moles of ethanol on bottom. And then this relationship is 44.01 grams of CO2 is 1 mole of CO2. And we want moles of CO2 on bottom, so 1. Calculating grams, moles of ethanol, moles of CO2, moles of CO2. We end up in grams CO2. Calculate this, get a number here. What's the other word for this? Theoretical yield. Our theoretical yield of CO2, 0.5 times 2 is 44.01 divided by 1s. No, it's 44.01. My calculator says .5 times 2 is 1, so we just get 44.01 back. But we only need 2 significant figures here. Exact, these are those coefficients from up there, so these are exact, that's exact. So 2 significant figures and 4 significant figures, so we're only keeping those. The answer is 44 grams. Does that make sense? So theoretical yield comes up below here somewhere in another section, so they didn't call it the theoretical yield. But when you're calculating theoretically how much of one of the products you're getting, that's theoretical yield. Let's do this one. What is this? Sample problem 5.17. Skip the environmental note. So let's do this one. How many grams of aspirin? We already did synthesis of aspirin in the lab, right? This is literally what we did. Although we used acetic anhydride. I'll do this one. C7H6O3. salicylic acid plus acetic acid, C2H4O2. C9H8O4. And then good old water. Okay, how many grams of aspirin? This is aspirin. Aspirin is sort of like the brand name of acetylsalicylic acid. Grams of aspirin, 10 grams of salicylic acid. So 10 grams of that is put in. How many grams of aspirin? So asking for grams. All right. Grams of salicylic acid and grams of aspirin. So we're going to need the grams per mole for both of these. It's a little tedious, but I'm going to call this SA. Salicylic acid. There's 7 carbons, there's 6 hydrogens, and that is a 3, right? For salicylic acid. I can't quite see it. I guess it's a 3. It looks weird up close. If you look on the periodic table, you see 12.01, 1.01, 16.00. Over here, we have 9 carbons, 8 hydrogens, 4 oxygens. 12.01, 1.01. Doesn't tell us, okay. 7 times 12.01. This is going to be 6.06. Anybody do 3 times 16 in their head quick? It's 48. So we've got to add those up. 9 times 12.01. This is going to be 8.8. This is 64. 32. So we're going to add that up. 87.07 plus 6.06 plus 141.13. This one is 108 plus 108.09 plus 8.8 plus 64. Okay. So we're going to use this and this in our calculation. This is with the units in the label. Is that salicylic acid is 141.13 grams of C7H6O3. You with me? I know it's tedious, but I don't think it's too complicated, it's just tedious. Of course, I don't think it's complicated, because I've been doing this for years. It still feels tedious, doesn't feel any less tedious. Is this all one-to-one relationship? It is. These are all just one-to-one relationship. So, 1 mole of this C9, H8O4. So we'll use that to be formal. So we'll start like this, 0 grams of C7H6O3, 10 grams of salicylic acid. We've got grams of C7, grams of the C7, that's got to be on the bottom. C7H6O3 to 1 mole of C7H6O3. So now we need moles of C7H6O3 at the bottom here, so it's this. Keeping it formal and putting this in there, just because these aren't always one-to-one, so I'm gonna put it in there. But also it makes the units cancel the way they should. So now I'm gonna have moles of C9, C9H8O4. Okay, almost there. Now we're gonna use this. Moles of C9, moles of C9, so this needs to be on the bottom. 1 mole of C9H8O4 to 180 grams of C9. Grams of C7, grams of C7. Moles of C7, moles of C7, moles of C9, moles of C9 end up in grams of C9H8O4, which is what we were after. Alright, so math. Times 180.17 divided by 141.13. The calculator says we're not going to use all those. So that's exact, that's exact. These are always exact. These coefficients are always exact. Those are those coefficients. That's exact. So we're down to 3 significant figures here, 5 significant figures here, 5 significant figures there. So we need 3 significant figures. You with me? Based on significant figures. The 6 rounds the 7 up. This 6 rounds the 7. So I'm going to say, that's the answer, 12.8 grams. On a test for something this big, I will probably just give you these instead of making you calculate them, so keep an eye out for that. Some of the problems I give you just gives you those two. It would only be for very small molecules I have you calculate it. But I might have a problem on its own that might have, say, what's the grams per mole for this? And if the rest of it, you were just calculating that, then I'd have you calculate it. But when it comes to a larger problem like this, I'm more likely to just give you these rather than you have to go over on a scratch piece of paper and work it all out. I'll test your ability to come up with these on a separate question. So, I think that's good. So we didn't get to limiting reactive, which is the very last thing in this chapter. I have to kind of pick and choose what's gonna go on test two. Oh. In the last couple of minutes. Housekeeping issue. I need to upload this because I've changed the schedule. I stuck spring break in here. And I want us to at least have that whole first week and then a day of review before test two. So this is the week after spring break, Tuesday and Thursday. I was gonna push test two forward, but I think I'm just gonna squeeze what I can in. And if I have to come back to chapter 5 or something, chapter 6 later, I will. But you'd be doing yourself a favor to go through all of these questions, these quiz questions, prior to spring break. So when you come back from spring break and have to wake your brain back up, you've already been through it all and you can just re-familiarize yourself. Because we will have to go over some new stuff that Tuesday and Thursday. All right, I guess that's it. Any questions? All right, I'll see some of y'all in lab. Other than that, happy spring break.
Did you?